Imagine something so powerful, it could race around the entire Earth in less than a second, not a sci-fi fantasy, but a reality lurking in the depths of space. Out there, beyond our atmosphere, cosmic objects move at speeds so staggering they defy comprehension. Take pulsars, for instance, spinning neutron stars that can rotate hundreds of times per second, their beams of light slicing through the darkness like interstellar lighthouses. Or quasars blazing with the energy of 1 trillion suns, hurling jets of matter at nearly the speed of light across millions of light years. These aren't just abstract wonders, they're the universe's ultimate speed demons, and they're rewriting the rules of physics as we know them. What if I told you that some stars don't just drift lazily through the galaxy, they get kicked out of it entirely? Hypervelocity stars, flung from the heart of the Milky Way by the gravitational slingshot of a supermassive black hole, race through the void at millions of miles per hour. And then there are the mysterious particles, born in the chaos of exploding stars or colliding galaxies, that hurtle through space with enough energy to punch through planets like they're made of tissue paper. These aren't just curiosities for astronomers, they're cosmic puzzles that challenge everything we think we know about speed, energy, and the limits of the universe itself. Today, we're diving deep into 30 of the most astonishing facts about the fastest objects in the cosmos. From the mind-bending velocities of rogue stars to the explosive power of relativistic jets, each of these phenomena tells a story of extreme forces and cosmic drama. Whether you're a seasoned space enthusiast or just someone who loves to marvel at the universe's grandest spectacles, this journey will leave you awestruck. So buckle up, because we're about to explore the outer edges of speed, where the laws of physics are pushed to their limits, and the universe reveals its most exhilarating secrets. Picture a star, not just any star, but one flung from its home galaxy with such violence that it streaks across the cosmos at over 1 million miles per hour. These aren't the serene twinkling lights we see from Earth. These are hypervelocity stars, celestial outcasts ejected by the universe's most brutal forces. The culprit, supermassive black holes lurking at galactic centers. When a binary star system wanders too close, one star gets captured by the black hole's gravity while the other is catapulted outward like a slingshot, an interstellar expulsion so powerful it defies imagination. Take US 708, the first hypervelocity star ever confirmed. Racing through space at 745 miles per second, it's moving so fast that it's not just leaving its galaxy behind, it's escaping the Milky Way's gravitational pull entirely. Astronomers spotted this cosmic speedster by studying its light. Just as a siren's pitch changes as an ambulance races past, starlight shifts color when a star moves toward or away from us. US 708's light stretched into the red end of the spectrum, betraying its breakneck retreat. What's even more astonishing is where these stars end up. Unlike most celestial objects bound by gravity's grip, hypervelocity stars are destined for the void between galaxies, a lonely, endless journey through the freezing darkness. Yet their trajectories aren't just cosmic accidents, they're clues. By tracing their paths backward, scientists can map the hidden forces at work in our galaxy's heart, unraveling the violent dance between stars and the monsters that lurk there. Now shift your gaze from runaway stars to something even more extreme, a cosmic object spinning so fast it turns physics into a high-stakes balancing act. Meet PSRJ 1748-2446 AD, the fastest spinning pulsar ever discovered. This neutron star, the crushed core of a once mighty sun, rotates an astonishing 716 times every second. To put that in perspective, if Earth spun that fast, our entire planet would complete a full rotation in less than 2 milliseconds, flinging everything into space like a cosmic centrifuge. What keeps this celestial dynamo from tearing itself apart? The answer lies in its mind-boggling density. a neutron star packs more mass than our Sun into a sphere barely the size of a city. That means its surface gravity is 100 billion times stronger than Earth, so powerful it warps the fabric of space-time itself, creating ripples known as gravitational waves. These waves carry energy away, acting like a cosmic brake that prevents the pulsar from spinning so fast it shatters. But here's the real marvel: these spinning powerhouses aren't just freakishly fast, they're nature's most precise clocks. As they rotate, they emit beams of radiation that sweep across space like lighthouse beams. Each flicker arrives with such regularity that astronomers can track them down to the nanosecond. Some pulsars keep time better than atomic clocks here on Earth. Their rhythms so stable they've even been used to test Einstein's theory of relativity. The story gets stranger. The reason we know this pulsar's speed so precisely is thanks to its partner, a small, dense star caught in a gravitational tango with it. As the two orbit each other, their interaction reveals details invisible to telescopes alone. It's a cosmic dance where gravity and speed collide, showing us that even the universe's most violent objects follow rules we're only beginning to decode. But the universe has even more breathtaking speed demons, colossal jets of superheated plasma rocketing from black holes at nearly the speed of light. These are relativistic jets, narrow beams of particles and energy launched from active galactic nuclei, where supermassive black holes feast on swirling disks of gas and dust. The most famous example, the monstrous black hole at the center of galaxy M87, which hurls a jet stretching 5,500 light-years into space. That's like a cosmic fire hose blasting material across a distance so vast it would take a spacecraft thousands of millennia just to traverse it, and the particles in that jet. They're moving at 99% the speed of light, so fast that time itself slows down for them due to Einstein's theory of relativity. How does a black hole, known for trapping even light, create such an unimaginably fast outburst? The secret lies in the chaos just outside its event horizon. As matter spirals toward the black hole, friction heats it to millions of degrees, turning it into a swirling soup of charged particles. Twisted magnetic fields, stronger than anything we could generate on Earth, act like cosmic railguns, channeling some of this material into tightly focused jets. The process is so efficient that particles get whipped to these extreme speeds in just a fraction of a second, nature's ultimate particle accelerator. What's truly mind-bending is how these jets shape the universe around them. When they slam into surrounding gas clouds, they trigger shock waves that can spark new star formation or snuff it out entirely. Some jets even bend under the influence of intergalactic winds, creating spectacular, ribbon-like structures visible across millions of light-years. And here's the kicker: we're seeing these jets as they were millions or billions of years ago, their light just now reaching us. That means we're glimpsing the violent adolescence of the cosmos, watching black holes reshape galaxies in real cosmic time. But M87's jet isn't just a cosmic curiosity, it's a Rosetta Stone for astronomers. In 2019, the Event Horizon Telescope captured the first ever image of a black hole's shadow, with the jet's base clearly visible. That image confirmed decades of theories about how black holes power these relativistic beams, giving us front-row seats to one of the universe's most extreme phenomena. And yet, for every answer, new questions emerge. Why do some black holes produce jets while others don't? How do particles in the jet avoid collisions that should slow them down? Each discovery peels back another layer, revealing just how little we truly understand about the universe's fastest, most furious engines. Black holes aren't just cosmic vacuum cleaners sitting motionless in space. Some are hurtling through the universe at unimaginable speeds, leaving chaos in their wake. Take CID-42, a supermassive black hole racing through its galaxy at nearly 5 million miles per hour. That's fast enough to cross the entire United States in less than a second. How does something with the mass of millions of suns get launched like a cosmic cannonball? The answer lies in one of the universe's most violent events, a galactic collision. When two galaxies merge, their central black holes eventually spiral toward each other, locked in a gravitational dance. As they get closer, they emit ripples in space-time called gravitational waves. If these waves aren't perfectly symmetrical, if one black hole is slightly more massive or spinning faster, the recoil can kick the merged black hole clear out of its galactic core. Think of it like firing a rifle. The bullet flies forward, but the gun kicks back with equal force. In this case, the bullet is a torrent of gravitational waves, and the kick sends the black hole careening into intergalactic space. Hubble's keen eye caught CID-42 in the act, a black hole so far from its expected location that astronomers knew something extraordinary had happened. Surrounding it, a trail of young, blue stars revealed its path, glowing like breadcrumbs left behind by a cosmic giant. These stars formed from gas shocked and compressed in the black hole's wake, a stunning side effect of its high-speed escape. Simulations show these runaway black holes can travel hundreds of thousands of light years from their birthplace, sometimes even leaving their host galaxies entirely. What's wild is that this isn't just a one-off event. Astronomers estimate that thousands of these rogue black holes could be lurking in the voids between galaxies, invisible except for the faint trails of stars or heated gas they leave behind. Some might even be drifting right through our cosmic neighborhood, their presence betrayed only by slight warps in the light of distant stars. And here's the twist: these nomadic monsters aren't just relics of the past. With countless galaxies destined to collide in the future, the universe will keep hurling black holes into the darkness, proving that even the heaviest objects in existence aren't immune to the cosmos's need for speed. While runaway black holes and relativistic jets push the boundaries of speed on galactic scales, something far smaller and faster is bombarding Earth right now from the depths of space. Cosmic rays, subatomic particles like protons or atomic nuclei, scream through the void at just a hair's breadth below light speed. When these invisible bullets slam into our atmosphere, they unleash cascades of secondary particles, a silent storm of energy that would be deadly if not for the protective shield of Earth's air. But one cosmic ray stands above all others, the Oh My God particle, detected in 1991 over Utah. This single proton packed a jaw-dropping 320 exaelectron-volts of energy, millions of times more powerful than anything produced in human-made particle colliders. To grasp just how absurd that energy is, imagine a baseball traveling at 60 miles per hour. Now scale that up to a proton moving at 99.9% the speed of light. It carried the kinetic energy of a fast-pitched baseball crammed into a particle tinier than an atom. That's like fitting the force of a freight train into a single grain of sand. Where could such an extreme particle come from? Astronomers point to the most violent events in the universe: supermassive black holes devouring stars, colliding neutron stars, or perhaps even supernovas with shocks powerful enough to act as cosmic particle accelerators. The truth is, we still don't know for sure. The Oh My God particle defies even our best models of physics, leaving scientists scrambling to explain how nature can hurl matter with such incomprehensible force. What's wild is that these particles aren't rare. Thousands strike Earth's atmosphere every second. Most are lower energy, but occasionally, another ultra-high-energy cosmic ray like the Oh My God particle arrives, leaving detectors blinking in disbelief. These events are so sporadic and unpredictable that scientists have built sprawling observatories like the Pierre Auger Array in Argentina, covering over 1,000 square miles to catch them in action. Each detection is like finding a cosmic fingerprint, a clue pointing back to some cataclysmic event billions of light years away. And here's the twist: these particles might be reshaping life on Earth in ways we're only beginning to understand. Some researchers suggest cosmic rays could influence cloud formation or even trigger genetic mutations over millennia. While the oh my god particle itself is harmless by the time it reaches the ground, its existence forces us to confront a humbling truth. The universe is filled with natural phenomena that dwarf anything we can create, reminding us that the cosmos still holds mysteries we've barely begun to unravel. The universe isn't just full of fast-moving objects, it's stretching the very fabric of space itself, carrying galaxies away from us at speeds that defy common sense. Here's the mind-bending truth: some galaxies are receding faster than light, not because they're moving through space, but because the space between us and them is expanding. This isn't science fiction, it's Hubble's law in action, a cornerstone of modern cosmology. The farther away a galaxy is, the faster it appears to race away from us, stretching its light into longer, redder wavelengths like a cosmic fingerprint of departure. Take a galaxy billions of light years away. Unlike a car speeding down a highway, it isn't burning fuel to accelerate. Instead, the space between us is growing like dots on an inflating balloon. The more space there is between dots, the faster they seem to separate. This expansion adds up over vast distances, eventually surpassing light speed for galaxies near the edge of the observable universe. And here's the twist: these galaxies aren't breaking any cosmic speed limits. Einstein's relativity only forbids objects from moving through space faster than light. Space itself can stretch faster, carrying galaxies along for the ride like leaves on a rushing river. The evidence for this is etched into starlight. When astronomers point telescopes at distant galaxies, they don't just see dim pinpricks, they see light stretched into the red part of the spectrum, a phenomenon called redshift. The greater the redshift, the faster the galaxy appears to flee. Some quasars, the luminous cores of ancient galaxies, show redshift so extreme their light left them when the universe was a fraction of its current age. Their light has been stretched so much that what was once visible ultraviolet now reaches us as faint infrared whispers, but there's a boundary to what we can see. Beyond a certain distance, space expands so fast that light from those galaxies can never reach us, a cosmic horizon hiding nearly all of the universe's expanse. Yet even this horizon isn't static. As expansion accelerates, driven by mysterious dark energy, more galaxies vanish beyond it every second, their light fading into oblivion as the universe grows ever lonelier. Hubble's law isn't just a curiosity, it's our window into the universe's past and future. By measuring redshifts, astronomers can reconstruct how fast space stretched at different epochs, tracing the cosmos's evolution from a fiery infancy to its current vast, cool expanse. And lurking in that data is an even deeper mystery, the force we call dark energy, which seems to be pushing galaxies apart faster and faster. The universe isn't just expanding, it's doing so on cosmic steroids, racing toward a future where distant galaxies will vanish from sight entirely, leaving only our local cluster adrift in an endless, empty dark. So the next time you gaze at the night sky, remember, those seemingly motionless stars and galaxies are part of a grand, rushing tapestry, woven by the unstoppable expansion of space itself. The universe isn't static, it's a living, breathing entity, stretching its limbs at speeds that humble even the fastest pulsars or hypervelocity stars. And with every passing second, it runs a little faster, carrying the secrets of the cosmos ever farther beyond our reach. Some planets don't just orbit their stars, they're strapped to a cosmic roller coaster, hurtling through space at speeds that would vaporize a spacecraft in seconds. At the top of this extreme leaderboard sits Kepler 70b, an exoplanet so close to its white dwarf host that it completes a full orbit in just 5 hours. That's not a typo. This world rockets around its star at 1.5 million miles per hour, a velocity so blistering it could lap Earth's entire circumference in under 10 seconds. What kind of star could anchor such a frenzied dance? Not the stable, sun-like stars we're familiar with. Kepler 70b's host is a white dwarf, the smoldering core of a dead star, packing half the Sun's mass into a sphere no larger than Earth. With gravity 100,000 times stronger than our planet's, this stellar corpse whips its planetary companion around like a slingshot, their mutual gravitational tango warping both bodies into egg-like shapes. Surface conditions here make Venus look like a winter retreat. Daytime temperatures soar to 7,000 degrees Celsius hotter than some stars, turning rock into vapor and metals into swirling supercritical fluids. The planet's atmosphere, long gone, stripped away by the white dwarf's relentless radiation and stellar winds. What remains is a bare, molten core, glowing like a blacksmith's forge as it endures ceaseless gravitational torture. But this doomed world won't last forever. Those same tidal forces driving its breakneck speed are also slowly sapping its orbital energy. With each pass, Kepler 70b spirals marginally closer to its star, destined for a fate straight out of astrophysical horror. One day, the white dwarf's gravity will overcome the planet's structural integrity, tearing it apart in a cataclysmic spaghettification event. The debris will rain down onto the star's surface, sparking fleeting flares detectable across interstellar space, a final, fiery epitaph for the fastest planet we've ever found. What's astonishing isn't just Kepler 70b's existence, but what it reveals about planetary survival. This planet likely started life much farther out, only to be pulled inward after its star's death throes. That it persists at all in such a hostile environment suggests planets might be far more resilient or far more numerous than we ever imagined. When we look up at the night sky, it's easy to picture orderly solar systems like our own. But Kepler 70b reminds us the cosmos has a flair for the extreme, crafting nightmares and wonders beyond our wildest dreams. Quasars aren't just dazzling beacons of light, they're cosmic powerhouses capable of unleashing storms so violent they can reshape entire galaxies. At the heart of these maelstroms lie quasar outflows, supersonic winds roaring through space at 20% the speed of light. Picture a hurricane with winds reaching 130 million miles per hour, but instead of rain and debris, it's a torrent of superheated gas and radiation, carrying more energy every second than a trillion stars combined. These aren't just space weather, they're galactic-scale bulldozers, carving out voids in interstellar gas and shutting down star formation across billions of miles. The mechanics behind these outflows are as mesmerizing as they are destructive. As matter spirals toward a quasar's supermassive black hole, friction heats it to millions of degrees, creating an accretion disk so luminous it outshines entire galaxies. But not all that material gets swallowed. Intense radiation and magnetic fields blast some of it outward, accelerating particles to relativistic speeds in a process so efficient it defies earthly physics. The result, a bipolar jet of plasma and radiation, screaming into the cosmos with enough force to push surrounding gas clouds out of the galaxy entirely. One of the most extreme examples lies in quasar SDSSJ 1106+1939, whose outflow travels at a staggering 47 million miles per hour. The energy here is almost incomprehensible, around 100 times the total output of the Milky Way, concentrated into a single, narrow beam. That kind of power doesn't just nudge interstellar material. It flings it into the void, stripping galaxies of the raw ingredients needed to birth new stars. Over millions of years, these outflows can transform a vibrant, star-forming galaxy into a quiet, aging husk, a process astronomers call quenching. Yet these violent winds aren't purely destructive. Paradoxically, they might be essential for galactic evolution. By clearing away excess gas, outflows prevent galaxies from growing too massive too quickly, potentially explaining why we don't see more super-sized galaxies in the modern universe. Some models even suggest these outflows redistribute heavy elements forged in the quasar's heart, seeding future generations of stars and planets with the building blocks of life. What's truly humbling is the scale of time and distance involved. When we observe these outflows, we're glimpsing events that began when the universe was less than half its current age, their light just now reaching us after eons of travel. And buried in that light are clues about how the most energetic objects in existence shaped the cosmos we see today. Far from being mere curiosities, quasar outflows are proof that even the most destructive forces in the universe can have a creative purpose, weaving chaos and order into the grand tapestry of galactic life. Gamma-ray bursts are the universe's ultimate fireworks, blinding flashes of energy so intense they outshine entire galaxies for a few fleeting seconds. But hidden within these cosmic detonations lies an even more astonishing phenomenon: narrow jets of matter screaming through space at 99.999% the speed of light. Picture a particle racing so fast it could circle Earth 7 times in a single second, or cross the distance to Pluto in under 30 minutes. That's the mind-numbing velocity of material ejected during a gamma-ray burst, nature's most extreme particle accelerator. Take GRB 080916c, a record-setting burst detected in 2008. Situated 12.2 billion light-years away, this cataclysm released more energy in 30 seconds than our Sun will emit over its entire 10 billion-year lifetime. But the real showstopper was its jets, twin beams of plasma so narrowly focused they'd appear pencil-thin from Earth, yet powerful enough to blast material across 99 billion miles in just 4 seconds. To put that in perspective, that's like traveling from New York to Sydney over 150,000 times before you could finish reading this sentence. What could possibly propel matter to such insane speeds? The answer lies in the death throes of massive stars. When a star dozens of times heavier than our Sun collapses, its core doesn't just form a neutron star or black hole. It triggers a hypernova, an explosion orders of magnitude more violent than a typical supernova. As the star's outer layers crash inward, they rebound off the newly formed core, creating shock waves that funnel escaping material into 2 opposing jets. Magnetic fields billions of times stronger than Earth's coil around these jets like cosmic springs, further accelerating particles to velocities Einstein himself might have found unbelievable. The physics gets wilder. At these speeds, strange relativistic effects dominate. Time dilation means that while 4 seconds pass for us watching from Earth, mere milliseconds tick by for particles in the jet. The radiation they emit gets squashed into incredibly high-energy gamma rays through a process called relativistic beaming, explaining why these bursts briefly outshine everything else in the universe. And here's the twist: we only detect gamma-ray bursts when one of these deadly narrow beams happens to point directly at Earth, making them far more common than we can observe. But GRB 080916c wasn't just fast, it rewrote the rulebook. Observations from NASA's a Fermi Gamma-Ray Space Telescope revealed its photons reached energies previously thought impossible for gamma-ray bursts, challenging theories about how particles behave under such extreme conditions. The burst's light also arrived in distinct waves, revealing staggered acceleration phases where different particle populations reached their peak speeds at slightly different times, like cosmic gears shifting in a hyperdimensional engine. What's truly humbling is that we're seeing these events unfold across cosmic time. GRB 080916c erupted when the universe was just 1.8 billion years old. Its light spent over 12 billion years traveling to reach our telescopes. That means we're glimpsing the violent adolescence of the cosmos, watching primordial stars die in spectacular fashion while their high-speed jets carve paths through the early universe. And somewhere out there, newer gamma-ray bursts are occurring right now, their light still en route, carrying secrets about the universe's most extreme speeds that we've yet to discover. For all its vastness and seeming stillness, our Milky Way galaxy isn't drifting aimlessly through space, it's being hauled toward something massive at 1.3 million miles per hour. That invisible, irresistible force dragging us through the cosmos, astronomers call it the Great Attractor, a gravitational anomaly so powerful it bends the paths of entire galaxy clusters toward it. Hidden behind the dense plane of our own galaxy, this mysterious region of space has puzzled scientists since its discovery in the 1970s, when peculiar motions in nearby galaxies revealed something enormous was pulling them and us off course. At the heart of the mystery lies an imbalance in the cosmic ledger. The Great Attractor's gravitational influence suggests it should contain the mass of tens of thousands of Milky Ways, yet visible matter, stars, gas, galaxies accounts for barely a fraction of that. So what's generating this staggering pull? Some theorize vast reservoirs of dark matter, the invisible scaffolding of the universe clustered there in unprecedented density. Others point to something even stranger, the possibility that the Great Attractor isn't the final destination, but just one stop on a far larger journey. Observations show our local galaxy cluster, along with countless others, is caught in what's called a dark flow, a collective movement towards something even more distant and massive, perhaps a supercluster of galaxies so enormous it defies current models of cosmic structure. Here's where the plot thickens. The Great Attractor sits near the center of the Laniakea supercluster, a web-like structure spanning 500 million light-years that contains 100,000 galaxies. Yet Laniakea itself appears to be in motion, tugged toward an even grander anomaly dubbed the Shapley Attractor, nearly 700 million light-years away. This cosmic tug-of-war suggests hierarchies of gravity we're only beginning to map, with each layer revealing larger and more influential structures. It's as if the universe is a series of nesting dolls, each hiding a deeper gravitational secret. What makes the Great Attractor especially fascinating is how it challenges our perspective. From Earth, its direction lies behind the Milky Way's central bulge, where thick dust clouds obscure our view like a cosmic curtain. Only with radio and infrared telescopes have astronomers pierced this veil, discovering unusual galaxy concentrations like the Norma cluster, which may contribute to the phenomenon. But the deeper we look, the clearer it becomes the Great Attractor might not be a single object, but the focal point of an immense convergence of matter, a gravitational watershed where the streams of cosmic structure flow together. One startling implication: this relentless motion means the distant future will look nothing like today's sky. Over billions of years, as the Milky Way and Andromeda merge and fall deeper into the Great Attractor's grasp, entire galaxy clusters will collide and coalesce. The night sky for civilizations of that era would be ablaze with the light of countless new stars, ignited by the chaos of these cosmic mergers. Yet even as we hurtle toward this unknown destiny, the Great Attractor reminds us how much we still don't understand about the universe's largest structures and the invisible forces sculpting them. Perhaps the most humbling thought is this: for all our certainty about Earth's place in space, we're still passengers on a galaxy in motion, swept along by currents of gravity we've only begun to chart. The Great Attractor isn't just a destination, it's a clue, pointing toward the hidden architecture of the cosmos and the possibility that even greater mysteries lie beyond. Orbiting so close they could fit inside Saturn, the two white dwarfs of HM Cancri perform a gravitational ballet at speeds that stretch the imagination. Every 5.4 minutes, these collapsed stars complete a full orbit around each other, racing through space at 310 miles per second, so fast they could cross the Atlantic Ocean in less time than it takes to microwave popcorn. Discovered in 2004, this binary system holds the record for the tightest orbit ever observed, a cosmic whirlwind where time and space warp under extreme conditions. One white dwarf is about the size of Earth but packs half the Sun's mass, while its partner is smaller but denser. Their proximity, separated by just 80,000 miles, a third the distance from Earth to the Moon, creates tidal forces so intense they've deformed both stars into teardrop shapes. As they whip around each other, their gravity distorts the fabric of space-time, generating ripples called gravitational waves that carry energy away from the system. This slow but steady drain ensures an inevitable fate. In roughly 300,000 years, the stars will spiral into each other in a cataclysmic merger, likely triggering a rare type Ia supernova or forming an even denser neutron star. What makes Cancri so special isn't just its speed, but how it proved Einstein right in spectacular fashion. The system's orbital period decreases by 1.1 milliseconds every year, a tiny but measurable shift perfectly matching predictions from general relativity. That precision turns these stars into a natural laboratory for testing physics under conditions no Earth-based experiment could replicate. The gravitational waves they emit, though too faint for current detectors to observe directly, subtly alter their orbit in ways telescopes can track, offering astronomers a front-row seat to spacetime's curvature in action. Cancri's dance also holds clues about the universe's hidden population of ultra-close binaries. Most white dwarf pairs form when aging stars shed their outer layers, often drifting apart. But in rare cases like this, interactions with other stars or planets can tighten their orbits over billions of years, creating these extreme systems. Some researchers suspect similar binaries might be the source of mysterious fast radio bursts or even serve as standard candles for measuring cosmic distances, their predictable mergers acting as celestial mileposts across the universe. Yet for all its scientific value, Cancri remains a fleeting spectacle on cosmic timescales. 300,000 years might sound like an eternity, but for stars that have existed for billions of years already, it's the blink of an eye. When the collision finally happens, the resulting explosion could outshine entire galaxies for weeks, briefly becoming one of the brightest objects in the universe. Until then, this pair serves as a reminder that even in death, stars can create some of the most breathtakingly fast and violent phenomena the cosmos has to offer. Right now, a cosmic neighbor is barreling toward us with unstoppable momentum, the Andromeda Galaxy, closing the distance at 250,000 miles per hour. That's fast enough to cross the entire United States in less than 10 seconds. But this isn't some rogue projectile on a collision course. It's the natural pull of gravity between two titanic structures, each containing hundreds of billions of stars. In roughly 4.5 billion years, the Milky Way and Andromeda will meet in one of the most spectacular events the local universe has ever seen, a slow-motion merger that will rewrite our galaxy's structure forever. Simulations of this cosmic dance reveal an astonishing future. Unlike the catastrophic crashes often depicted in movies, galaxies don't collide like bumper cars. They merge like swirling ink drops in water. As Andromeda's gravitational tides distort the Milky Way spiral arms, both galaxies will stretch and warp, throwing stars into chaotic new orbits. Yet here's the counterintuitive part. Despite the monumental scale of this event, direct star-to-star collisions will be vanishingly rare. Space is so vast that even when galaxies interpenetrate, most stars will glide past each other untouched, like two flocks of birds mingling in midair. The real fireworks will happen in the gas clouds. As these dense regions slam together, shockwaves will trigger bursts of star formation so intense they'll outshine the combined light of both galaxies' cores. Imagine millions of new stars igniting in brilliant blue clusters, a stellar baby boom lighting up the night skies of any surviving planets. Over time, the two supermassive black holes at their centers, Andromedas, weighing 100 million suns, and our own Sagittarius, a star, will begin a gravitational tango, circling each other for millions of years before finally merging in a space-time shaking event that will send gravitational waves rippling across the cosmos. What emerges from this billion-year process won't resemble either original galaxy. Computer models suggest the result will likely be a massive elliptical galaxy, its stars orbiting in random directions like a beehive swarm rather than the orderly spiral we know today. Some simulations even nickname this future hybrid Milkdromeda, a cosmic mashup where the Sun, if it still exists, might find itself flung far from the galactic suburbs into uncharted territory. Yet for all the drama, this collision is more of a reunion than a catastrophe. Andromeda and the Milky Way have likely grazed each other before, nearly 10 billion years ago, when both were smaller and still forming. Their impending merger isn't an anomaly. It's business as usual in an evolving universe where galaxies grow by consuming their neighbors. In fact, our own Milky Way bears scars from past galactic meals, with streams of stars still tracing the orbits of galaxies it absorbed billions of years ago. The most humbling realization: this entire process is already underway. While 4.5 billion years sounds unfathomably distant, the light we see from Andromeda tonight left it 2.5 million years ago, meaning it's already traveled much closer since those photons began their journey. Every second, the gap shrinks by another 70 miles, an inexorable drift we're powerless to stop. So next time you gaze at Andromeda's faint smudge in the night sky, remember, you're looking at our galaxy's future partner, hurtling toward us in a slow motion embrace written into the fabric of gravity itself. If you thought our Milky Way's spiral arms moved fast, wait until you hear about NGC 4889, the fastest spinning spiral galaxy ever discovered. Nestled in the Coma Cluster 300 million light-years away, this cosmic whirligig has outer stars screaming through space at 1.3 million miles per hour, nearly twice the speed of our galaxy's fastest stellar travelers. But what's really baffling astronomers isn't just the velocity, it's how this galaxy manages to hold itself together without flinging stars into the void. The secret lies in an invisible cosmic scaffold, dark matter. While our Milky Way's rotation can largely be explained by the visible stars and gas we observe, NGC 4889's outer stars orbit so fast that Newtonian physics says they should have escaped long ago. The only possible anchor, a dark matter halo so massive it makes our galaxies look like a faint shadow. Current estimates suggest this unseen structure contains 30 times more mass than all NGC 4889 stars, gas and dust combined, a gravitational glue strong enough to reign in those hypervelocity stars. Here's where it gets weird. Unlike most galaxies where rotation speeds taper off with distance, NGC 4889's outer stars maintain breakneck velocities far from the core, a phenomenon that flatly contradicts predictions based on visible matter alone. This discrepancy, first noted by astronomer Vera Rubin in the 1970s when studying other galaxies, became one of the earliest smoking guns for dark matter's existence. In NGC 4889's case, the effect is dialed up to 11, forcing scientists to reconsider just how much dark matter a single galaxy can harbor. The implications ripple far beyond one unusual galaxy. If NGC 4889's dark matter halo is this dense, it suggests these invisible structures might come in a broader range of configurations than we thought, some wispy, others almost unfathomably massive. That variability could explain why certain galaxies evolve into bustling spirals like ours while others become featureless ellipticals. It also raises tantalizing questions about how dark matter interacts with itself and ordinary matter over cosmic timescales. Zooming in closer, the galaxy's inner regions reveal another puzzle. While its outer stars race at record speeds, the core rotates relatively slowly, creating a peculiar velocity gradient unlike anything seen in nearby spirals. Some theorists propose this could be the aftermath of a past galactic merger, like a spinning ice skater pulling their arms in, but on a scale spanning hundreds of thousands of light years. Others speculate the galaxy's supermassive black hole, one of the largest known, might be influencing the dance through gravitational nudges we don't yet fully understand. What makes NGC 4889 especially fascinating is that it's not alone. Several other ultra-fast spirals have been spotted in dense galaxy clusters, suggesting extreme rotation might be more common in these crowded cosmic neighborhoods. The prevailing theory, cluster environments strip away galaxies' outer gas over time, leaving behind dark matter-dominated skeletons where stars can whirl at unprecedented speeds without the drag of interstellar material. For astronomers, this galaxy is more than a record holder. It's a natural laboratory for probing dark matter's elusive properties. By mapping the minute gravitational tugs between NGC 4889 and its neighbors, researchers hope to reconstruct the invisible scaffolding shaping its motion. Each measurement peels back another layer of the mystery, reminding us that for all its breathtaking speed, the galaxy's true story is written in the dark. Our solar system isn't just drifting peacefully through space, it's racing around the Milky Way's core at a blistering 514,000 miles per hour. That's fast enough to cross the entire United States in under 10 seconds, or complete a full orbit every 230 million years. Yet despite this dizzying speed, we don't feel a thing, carried along like passengers on a smooth cosmic train where the tracks are woven from gravity itself. This galactic journey leaves its mark in subtle but profound ways. Over millennia, the sun's motion shifts our vantage point enough to redraw the night sky's map entirely. Ancient Egyptian stargazers wouldn't recognize our modern constellations. The familiar Big Dipper, for instance, looked more like a spear to them 3,500 years ago. Fast forward another 50,000 years, and those same stars will stretch into a shape none of us would identify, their patterns warped by our solar system's ceaseless orbit. Even Polaris, our current North Star, will abdicate its throne as Earth's axis gradually tilts toward other celestial markers. In 12,000 years, the bright star Vega will take its place, a reminder that the cosmos never stands still. What's truly mind-bending is how this motion affects our place in the galaxy. Right now, we're about 27,000 light-years from the Milky Way center, orbiting within the Orion Arm, a relatively quiet suburban neighborhood where stars are spaced far enough apart to avoid catastrophic collisions. But as we hurtle forward, the sun bobs up and down through the galactic plane like a carousel horse, completing a full vertical oscillation every 64 million years. Some scientists speculate these periodic journeys above and below the denser disk might influence Earth's climate, as we pass through regions with varying cosmic ray exposure that could affect cloud formation or atmospheric chemistry. The mechanics behind this motion reveal the Milky Way's hidden architecture. Our speed isn't arbitrary, it's precisely tuned to balance the gravitational pull of everything inside our orbit: stars, gas clouds, and vast amounts of invisible dark matter. Just as planets move faster when closer to the sun, stars nearer the galactic center whip around at even more extreme velocities. The record holder, a star called S2, which screams past the Milky Way's supermassive black hole at 11 million miles per hour, completing an orbit in just 16 years. Yet for all its grandeur, this orbital dance is far from solitary. The entire Milky Way is in motion too, hurtling toward Andromeda at 250,000 miles per hour while being tugged by the great attractor's immense gravity. It's a universe where nothing stands still, not stars, not galaxies, not even the fabric of space itself. Every second, the sun carries us another 143 miles along this cosmic path, tracing an ellipse so vast it makes human history seem like the blink of an eye. So the next time you gaze at the stars, remember, those seemingly fixed points of light are part of a dynamic celestial ballet, with our solar system gliding through the galaxy's grand design. The constellations we learn today are mere snapshots in an ever-changing cosmic film. Their shapes were written by the silent, unstoppable motion of our star's galactic voyage. Far from being passive observers, we're active participants in this journey, hurtling through space on a planet, around a star, within a galaxy that never stops moving. After hurtling through space at a record-breaking 430,000 miles per hour, NASA Parker Solar Probe proudly holds the title of humanity's fastest spacecraft, but in the Cosmic Speed League, that's barely a leisurely stroll. Picture this: while the probe could cross the continental United States in under 20 seconds, the hypervelocity stars we discussed earlier would make the same trip in less time than it takes to blink. Even our speediest human-made object moves at just 0.064% of light speed, putting us firmly in the universe's slow lane. The Parker Solar Probe's achievement is undeniably impressive. It withstands temperatures hotter than lava as it dives through the sun's scorching corona, gathering data that rewrites solar physics textbooks. Yet nature's particle accelerators like quasar jets and gamma-ray bursts casually fling matter at 99.999% light speed without breaking a sweat. It's the difference between a firecracker and a supernova, a reminder of how far our engineering still has to go before matching the cosmos's raw power. Here's the kicker: the energy required to push the Parker probe to its current speed is roughly equivalent to 60,000 grown men throwing baseballs at full force simultaneously. Meanwhile, a single magnetar, a type of neutron star with an ultra-strong magnetic field, can unleash a flare in 1/10 of a second that carries more energy than our sun emits in 100,000 years. The universe doesn't just outperform our best efforts, it humbles them on scales we're only beginning to comprehend. But before we despair at humanity's snail-like pace, consider this: the Parker probe isn't just fast by our standards, it's a revolutionary leap in precision. While cosmic speed demons rely on unfathomable forces like black holes and supernova, our tiny spacecraft navigates within 4 million miles of the sun's surface using nothing more than gravity assists and a heat shield no thicker than a textbook. That's the beauty of human ingenuity. We might not have the universe's raw power, but we're learning to work with its rules, turning celestial mechanics into a playground for exploration. The next time you hear about a breakthrough in space travel, remember, even our wildest speeds are just baby steps in a galaxy where the laws of physics regularly bend the limits of imagination. The universe's fastest objects aren't just faster, they're playing an entirely different game, one where energy, velocity, and scale defy everything we know. And yet, with each mission like the Parker Solar Probe, we're inching closer to understanding how those rules work, one painstakingly engineered mile per hour at a time. When a star explodes, it doesn't just vanish in a flash, it leaves behind ripples of light that echo through space for decades. Supernova remnants like SN 1987 don't simply fade away. They race outward at 30,000 miles per second, lighting up surrounding gas like cosmic fireworks frozen in time. This particular stellar explosion, witnessed in 1987, gave astronomers a front-row seat to one of the universe's most dazzling light shows, not just from the initial blast, but from shockwaves that continue to illuminate interstellar material nearly 40 years later. What makes SN 1987 so special are those eerie, glowing rings that appeared years after the explosion. At first glance, they might look like static halos, but they're actually echoes, bursts of light from the supernova bouncing off shells of dust the star ejected centuries before its death. Imagine tossing a stone into a pond, then watching the ripples reflect off submerged branches. Now scale that up to cosmic proportions, where the pond is light years of space and the branches are vast nebulous structures. When ultraviolet radiation from the supernova finally reaches these pre-existing dust layers, it makes them fluoresce with delayed brilliance, creating luminous rings that expand like a time lapse of the original explosion. But the real speed demons here are the shockwaves plowing through space. As the supernova's debris slams into surrounding gas at 10% light speed, it generates temperatures of millions of degrees, hot enough to strip electrons from atoms and produce X-rays visible across intergalactic distances. Tantalizingly, Hubble caught one of these shockwaves colliding with a dense knot of gas in 2004, triggering a string of pearls, a line of 20 glowing hotspots where the shock ignited pockets of material. Each pearl represented a mini explosion, a chain reaction of stellar material slamming into the interstellar medium with enough force to outshine entire star clusters. What's astonishing is how these echoes serve as cosmic clocks. By tracking the expansion of SN 1987A's rings, astronomers can precisely measure both the distance to the supernova and the structure of the space it's traversing. The inner ring, now over 1 light-year across, reveals intricate details about the star's final millennia when it shed massive amounts of gas in episodic outbursts. Meanwhile, the shockwave speed, unchanged for decades, confirms theories about how supernova remnants interact with their environment, offering clues about how these explosions enrich galaxies with heavy elements. Here's the twist: we're seeing this aftermath unfold in what amounts to cosmic slow motion. The original light from the explosion took 160,000 years to reach Earth, but the echoes we observe today represent just a few decades of real-time evolution. It's like watching a single frame from a movie. Every year, each new observation adds another piece to the puzzle, showing how the universe processes stellar death on timescales humans can actually grasp. And somewhere out there, newer supernovae are creating their own light echoes right now, their shockwaves racing through space at speeds that defy imagination, painting the darkness with fleeting portraits of stellar destruction. Hanging like a celestial river across the southern sky, the Magellanic Stream arcs through intergalactic space at 217 miles per second, a vast ribbon of gas stretching over 300,000 light-years. This cosmic filament isn't just drifting aimlessly. It's being violently torn from the Magellanic Clouds, 2 small galaxies orbiting our Milky Way, in a gravitational tug of war that's been raging for billions of years. Picture a cosmic game of crack the whip, where the Milky Way's immense gravity pulls streams of hydrogen from these satellite galaxies, leaving behind a glowing trail that astronomers first detected in radio waves back in 1972. What makes this structure extraordinary isn't just its speed, it's the sheer scale of destruction and creation happening simultaneously. As the large and small Magellanic Clouds dance around our galaxy, their mutual gravity and the Milky Way's tidal forces stretch them like taffy, stripping away enough gas to form millions of stars. Yet this isn't just loss for the smaller galaxies, it's gain for ours. Detailed observations reveal the stream contains enough material to fuel star formation in the Milky Way for hundreds of millions of years, a slow-motion delivery of cosmic building blocks funneling toward our galaxy's future stellar nurseries. Radio telescopes have mapped the stream's intricate structure, showing it isn't a smooth river but more like braided rapids, with clumps and filaments shaped by magnetic fields and collisions with sparse intergalactic gas. Some segments glow brighter where fresh gas gets pulled from the cloud's outer disks, while older sections fade as they disperse into the galactic halo. The fastest-moving gas actually outpaces the Magellanic Clouds themselves, racing ahead like water droplets flung from a spinning wheel, evidence of gravitational boosts from past close encounters with our galaxy. Here's the twist: this cosmic theft isn't one-sided. Recent simulations suggest the Magellanic Clouds might be pulling some gas back too, creating complex loops and tendrils that weave between all 3 galaxies. It's an intricate gravitational ballet where material changes hands multiple times before finally settling into the Milky Way's orbit. Future telescopes like the Square Kilometre Array will track these movements in unprecedented detail, revealing how galaxies grow by stealing from their neighbors over cosmic timescales. The stream's ultimate fate, slowly spiraling down toward our galaxy's disk, where its hydrogen will eventually merge with Milky Way's gas clouds. When that happens, likely tens of millions of years from now, this recycled material could ignite new generations of stars, some perhaps with planets harboring life. Every atom in that stream carries a history spanning billions of years and multiple galaxies, a reminder that even the fastest-moving structures in our cosmic neighborhood are part of a slower, grander cycle of destruction and rebirth. In October 2017, astronomers spotted something unprecedented, a visitor from interstellar space racing through our solar system at 196,000 miles per hour. Named Oumuamua, Hawaiian for scout, this strange object defied all expectations. Unlike typical asteroids bound to the sun's gravity, Oumuamua moved fast enough to escape our solar system entirely, tracing a hyperbolic path that confirmed its extrasolar origin. But what made this cosmic interloper truly remarkable wasn't just its speed. It was the series of peculiar behaviors that followed. First, there was its shape. Observations suggested Oumuamua wasn't round or lumpy like most asteroids, but elongated, perhaps 10 times longer than it was wide, tumbling end over end like a flipped pencil. Then came the real shocker. As it sped away, it showed a slight but measurable acceleration, something rocky bodies don't typically do without an obvious push. The absence of outgassing, the telltale jets of gas that comets produce, only deepened the mystery. These oddities sparked intense debate. Some scientists proposed that Oumuamua could be a fragment of a larger body torn apart by tidal forces near a distant star, its weird acceleration caused by hidden vents expelling gas we couldn't detect. Others suggested it might be a chip off a Pluto-like world, rich in nitrogen ice that sublimated invisibly as it warmed. Then came the more speculative, but not entirely dismissible idea: could Oumuamua be artificial? The notion wasn't pulled from thin air. The object's unusual trajectory and unexpected speed boost loosely fit what we'd expect from a lightweight solar sail, a hypothetical spacecraft propelled by sunlight. Harvard astronomer Avi Loeb famously explored this angle, arguing that while natural origins were more likely, we shouldn't rule out the possibility of alien technology without evidence. The scientific community largely remains skeptical, favoring natural explanations. After all, the universe has a knack for producing phenomena weirder than fiction. What's undeniable is that Oumuamua forced us to confront how little we know about interstellar objects. Since its discovery, we've spotted more visitors like the comet Borisov, each offering new clues about the building blocks of other star systems. What lingers, though, is the tantalizing thought that somewhere in the vastness between stars, objects might be traveling not just by chance but by design. Whether Oumuamua was a bizarrely shaped rock or something more, its fleeting passage reminded us that the cosmos still holds surprises capable of shaking even the most grounded assumptions. Far out in the cosmos, entire galaxies can erupt in furious bursts of creation and destruction, hurling storms of gas into intergalactic space at 2 million miles per hour. These aren't just cosmic breezes, they're galactic superwinds, titanic outflows shaped by the combined fury of thousands of exploding stars. At the heart of this phenomenon lies Messier 82, a starburst galaxy 11 million light-years away where stars form 10 times faster than in our Milky Way, igniting chain reactions that blast raw material across hundreds of thousands of light-years. Peer at M82 through a telescope, and you'll see why astronomers call it the cigar galaxy, not just for its elongated shape, but for the plumes of smoke like filaments billowing from its core. These aren't gentle wisps, they're shockwaves from supernova so frequent they create a collective blast wave, heating gas to millions of degrees and driving it outward at speeds that dwarf anything in our solar system. The force is staggering, equivalent to detonating 30 suns worth of TNT every second for millions of years, a sustained eruption that sculpts the galaxy's surroundings like a cosmic sandblaster. What makes superwinds truly transformative is what they carry. As these outflows race through space, they're laden with heavy elements forged in stellar furnaces and supernova explosions: oxygen, carbon, iron, even gold. Like cosmic gardeners, they scatter these seeds of planet-building material far beyond their home galaxy, enriching the sparse gas between galaxies with the ingredients for future stars, planets, and perhaps life. Some of the iron in your blood likely originated in such a starburst wind billions of years ago, ejected by a dying star before our sun even existed. The mechanics behind these outflows reveal nature's balancing act. In starburst galaxies like M82, so many massive stars ignite in such a small region that their combined radiation pressure and supernova shocks overpower the galaxy's gravity. Gas that might have formed new stars gets expelled instead, regulating the galaxy's growth in a self-limiting cycle. It's a reminder that even in the universe's most extreme environments, feedback loops maintain equilibrium, violent as they may be. Here's the twist: these superwinds don't travel forever. Eventually, they collide with intergalactic gas, creating vast shock fronts that glow in X-rays. In M82's case, the wind has punched holes in surrounding hydrogen clouds, creating bubbles visible in radio telescopes. Over eons, some of the ejected material may rain back down onto the galaxy in a process called galactic recycling, while the rest merges with the cosmic web, becoming part of the intergalactic medium's chemical tapestry. What we're witnessing is more than just destruction, it's a vital part of cosmic evolution. Without these superwinds, galaxies would burn through their gas too quickly, leaving the universe devoid of the diversity we see today. They're the universe's way of stirring the pot, ensuring that the elements essential for life don't remain locked in one place but get distributed across the vast expanses between galaxies, ready to spark new beginnings billions of years later. Among the universe's fastest particles, neutrinos reign supreme, ghostly subatomic travelers so swift they flirt with the absolute speed limit of reality itself. Born in the nuclear furnaces of stars and the cataclysmic deaths of supernova, these nearly massless particles routinely hit 99.999% the speed of light, making them some of the most relentless speed demons in existence. When a star explodes, it doesn't just blast debris outward, it floods the cosmos with countless trillions of neutrinos, each streaking through space so fast they outpace their own star's visible light by hours. The detection of these particles from supernova 1987 are offered stunning proof of their blistering velocities. 3 hours before the dying star's light reached Earth, neutrino observatories registered a sudden spike, 23 ghostly particles arriving in rapid succession after their 160,000-year journey. That 3-hour head start wasn't due to laziness on light's part, but a brutal cosmic efficiency test. While photons struggled through the supernova's dense outer layers, neutrinos slipped through effortlessly, barely noticing the stellar material in their path. Their journey confirmed what physicists had long suspected, that neutrinos, despite their vanishingly small mass, obey Einstein's cosmic speed limit with near-perfect precision. Yet this elegant narrative nearly unraveled in 2011 when the opera experiment made headlines with an earth-shaking claim: neutrinos traveling faster than light. Their measurements suggested these particles had outpaced photons by 60 nanoseconds over a 454-mile underground path between Switzerland and Italy. The implications were staggering if true. This would shatter a cornerstone of modern physics, but science has a way of self-correcting. Months of scrutiny revealed the culprit: a loose fiber optic cable and an improperly synchronized atomic clock. The faster-than-light neutrinos were nothing more than measurement error, reaffirming Einstein's century-old theory. What makes neutrinos such fascinating speedsters isn't just their velocity, but how they achieve it. Unlike bulkier particles that require tremendous energy to approach light speed, neutrinos, with masses millions of times smaller than electrons, can hit 99.999% light speed with relatively modest boosts. In a supernova's core, where temperatures exceed 100 billion degrees, protons and electrons get crushed into neutrons, releasing neutrino bursts with energies dwarfing anything human accelerators can produce. These particles then race outward at such extreme speeds that relativistic time dilation comes into play. While thousands of years pass in the outside universe, a neutrino's subjective travel time could feel like mere minutes. The opera incident, though ultimately debunked, left a valuable legacy. It showcased science's capacity for rigorous self-examination. When faced with paradigm-shifting results, the physics community didn't simply accept or reject them. They tested, retested, and traced every possible variable until the anomaly was explained. This process, messy as it was, ultimately strengthened confidence in relativity rather than undermining it. Today, neutrino observatories like IceCube in Antarctica continue monitoring these cosmic speedsters, using their precise travel times not just to study particle physics, but to probe supernova mechanics, test quantum gravity theories, and even hunt for dark matter interactions. So the next time you hear about a high-speed particle, remember, the universe's true speed champions aren't the showy quasars or hypervelocity stars we can see, but the ghostly neutrinos slipping unnoticed through your body right now, trillions every second, each carrying whispers of distant stellar explosions, each a testament to nature's mastery of near-light-speed travel. Their silent, relentless motion through space and time reminds us that even in a universe teeming with fast objects, none dance closer to the edge of possibility than these shadowy cosmic messengers. While most cosmic objects take their time spinning through space, one misfit brown dwarf, 2-mass J0348-6022, crams a full rotation into just 1 hour. That's 200,000 miles per hour at its equator, a breakneck speed that flirts with the very limits of what's physically possible before gravity loses its grip entirely. This cosmic speedster, discovered in 2017, spins so fast that it's flattened like a pancake, its equator bulging outward from centrifugal force while its poles squeeze inward under the strain. What makes this failed star especially fascinating isn't just its dizzying spin, it's how narrowly it escaped becoming a true star at all. Brown dwarfs occupy the awkward gap between planets and stars, lacking the mass to ignite sustained hydrogen fusion in their cores. At around 75 times Jupiter's mass, 2-mass J0348-6022 sits right on the edge of stardom. Had it accumulated just a bit more gas during its formation, the increased pressure in its core might have tipped it over the threshold into full stellar status. Instead, it's stuck in cosmic limbo, too massive to be a planet, but not quite massive enough to shine like a star, its rapid rotation serving as a permanent reminder of its near miss. Scientists suspect this brown dwarf's extreme speed stems from a rebellious youth. Unlike stars, which typically slow down as they age due to magnetic braking and stellar winds, this object likely formed from a collapsing gas cloud that conserved its angular momentum with freakish efficiency. Imagine a figure skater pulling their arms in during a spin, except in this case, the skater started spinning wildly and never stopped. The result is a celestial object where a day passes in the time it takes to watch an episode of your favorite show, with equatorial winds howling at velocities that would strip any atmosphere to ribbons. Here's where physics throws a curveball. This brown dwarf shouldn't exist in its current state. According to rotational breakup models, an object of its mass and composition should tear itself apart at speeds just 10% faster than what we observe. Yet somehow, it persists, likely stabilized by internal density variations or magnetic fields we don't fully understand. It's a cosmic balancing act, spinning precariously close to the edge of stability while defying expectations. For astronomers, 2-mass J0348-6022 is more than just a record holder. It's a natural laboratory for testing the upper limits of rotational physics. By studying its light variations and spectral features, researchers can probe how atmospheric dynamics behave under such extreme conditions, offering clues about weather patterns on faster spinning exoplanets we might discover in the future. Every flicker in its brightness, every shift in its spectrum tells a story of a universe that constantly pushes boundaries, crafting objects that challenge our understanding of what's possible. Perhaps most intriguing is what this brown dwarf implies about the diversity of cosmic spin rates. If an object this massive can rotate so rapidly without disintegrating, what other extremes might be lurking in the dusty corners of our galaxy? From pulsars to gas giants, the universe seems to delight in creating spin-powered oddities, each one rewriting the rules in ways we're only beginning to comprehend. When two neutron stars collide, they don't just merge, they detonate in a cataclysmic explosion so violent it briefly outshines entire galaxies, the aftermath. A kilonova, a cosmic forge where matter gets hurled into space at 30% the speed of light. That's 200 million miles per hour, carrying with it the seeds of precious metals like gold and platinum. The historic GW170817 event, detected in 2017, gave us a front-row seat to this spectacle, proving that the universe's most dazzling jewelry stores aren't on Earth, but in the hearts of dying stars. Gravitational wave observatories felt the space-time ripples first, a faint chirp signaling two ultra-dense neutron stars spiraling toward each other. Seconds later, telescopes caught the fireworks show, a burst of gamma rays followed by a rapidly brightening glow across multiple wavelengths. What made this kilonova special wasn't just its speed, but its chemistry. As the neutron stars shredded each other apart, their exotic matter, a soup of neutrons and protons under unimaginable pressure, got flung outward in ultra-fast jets. Within seconds, nuclear reactions transformed this debris into heavy elements via a process called rapid neutron capture, or the R process. Here's the cosmic alchemy at work. Free neutrons, abundant in the merger's chaotic environment, bombard atomic nuclei faster than the nuclei can decay. Like stuffing a piñata to the point of bursting, this neutron overload builds unstable atoms that then decay into stable, precious metals. The numbers are staggering. A single kilonova can produce hundreds of Earth masses worth of gold and platinum in moments, scattering them across interstellar space at velocities so high they'd cross the Moon's orbit in under 7 seconds. The GW170817 event didn't just confirm theoretical predictions, it rewrote them. Spectroscopic analysis revealed telltale signatures of strontium in the ejector, proving kilonovae contribute to lighter heavy elements alongside the expected gold and platinum. Even more astonishing, the debris expanded asymmetrically, with some material racing outward faster than the rest, suggesting the merger didn't just explode, it erupted in a directional fury like a cosmic shotgun blast. But the real surprise was how quickly everything unfolded. From initial collision to peak brightness took mere days, a blink compared to supernova's weeks-long crescendos. That speed, combined with the ejector's extreme velocity, means kilonova material doesn't linger, it floods surrounding space almost instantly, seeding future generations of stars and planets with the raw ingredients for everything from dental fillings to spacecraft components. What's humbling is realizing how much of Earth's precious metals might owe their existence to such violent origins. The gold in your wedding ring or the platinum in a catalytic converter could be recycled stardust from a neutron star collision that occurred billions of years before our solar system formed. Every time humanity prizes these metals, we're holding pieces of the universe's most extreme physics experiments, remnants of explosions so powerful they briefly bend the rules of reality, then vanish, leaving behind cosmic treasure scattered across the light years. Most stars fade quietly into the cosmos, but not LP40-365. This white dwarf is rocketing through the Milky Way at nearly 2 million miles per hour, a speed so extreme it's escaping our galaxy entirely. What makes this stellar remnant extraordinary isn't just its velocity, it's the dramatic origin story written across its surface in glowing metallic signatures. Unlike typical white dwarfs cooling embers of dead stars, this runaway carries the chemical scars of a supernova that only partially destroyed it, making it the first known survivor of a failed stellar explosion. The physics behind this cosmic escape reads like a celestial heist gone wrong. Most white dwarfs form when stars like our Sun shed their outer layers, leaving behind a dense Earth-sized core. But LP40-365 was once part of a binary system, siphoning material from its companion until it grew unstable. Instead of triggering a standard supernova, the detonation blew away just enough mass to send the remnant careening into space while leaving the core intact, a cosmic slingshot effect with unprecedented violence. The recoil from this uneven explosion launched the white dwarf at triple the speed of most galactic stars, its trajectory cutting across the Milky Way like a bullet through smoke. What really sets this speedster apart is its bizarre composition. While normal white dwarfs have atmospheres dominated by hydrogen or helium, LP40-365's surface glows with heavier elements: neon, oxygen, magnesium, even traces of calcium and iron. These metals aren't just leftovers, they're the exposed innards of a star that literally blew its outer layers off, revealing the fusion-forged layers beneath. Picture a tree stripped of its bark by a hurricane, the concentric growth rings suddenly exposed to the open air, except in this case, the rings are stratified stellar material that should never have seen the light of space. Astronomers discovered this rogue traveler's secrets through spectroscopy, analyzing how its light breaks into distinct colors that reveal its chemical makeup. The data showed extreme metal enrichment alongside shock-heated gas trailing behind it, like a cosmic contrail marking its path through interstellar space. Even its temperature defies expectations: over 30,000 degrees Fahrenheit, far hotter than typical white dwarfs its age, as if the trauma of its birth left it permanently feverish. The implications ripple far beyond one bizarre object. LP40-365 proves that supernova can fail catastrophically yet leave remnants behind, rewriting models of stellar death. Its existence suggests there could be an entire population of similar hypervelocity white dwarfs streaking through the galaxy, each carrying tales of partial destruction in their elemental fingerprints. Some might even be remnants of Type Ia supernova, the explosions used to measure cosmic distances, raising questions about whether we've misunderstood these critical, standard candles of astronomy. As it flees the Milky Way, this stellar fugitive offers one final surprise. Its trajectory suggests it's been traveling for about 5 million years, yet shows no signs of slowing. In another 100 million years, it will have left our galaxy entirely, becoming a lone wanderer in the void between galactic islands. The atoms now racing toward intergalactic space will outlast the Milky Way itself, silent witnesses to a stellar explosion that couldn't quite finish the job, carrying the story of its violent birth across eternity. Most comets that dare approach the Sun meet a fiery demise, but Comet Lovejoy laughed in the face of solar destruction. In December 2011, this icy traveler did the unthinkable. It plunged directly through the Sun's multi-million-degree corona at 1.3 million miles per hour, emerging battered but intact on the other side. This kamikaze dive defied every expectation. Scientists had predicted complete vaporization. Yet Lovejoy survived its solar skydive with only partial damage, rewriting our understanding of cometary resilience in the process. The numbers behind this feat are staggering. As Lovejoy grazed just 87,000 miles above the Sun's surface, closer than Mercury's orbit, it endured temperatures exceeding 2 million degrees Fahrenheit. At that distance, the Sun's gravity accelerated the comet to speeds that could cross the continental United States in under 10 seconds. But the real surprise wasn't the velocity. It was how Lovejoy's nucleus, estimated at just 600 feet wide, withstood forces that should have torn it apart instantly. Most comets disintegrate 10 times farther away, making this the equivalent of a snowball surviving a blowtorch at point-blank range. What saved Lovejoy? The answer lies in the deceptive nature of the Sun's corona. While the corona's plasma reaches extreme temperatures, its particles are so sparse that heat transfer occurs slowly. Think walking through a hot oven rather than diving into molten lava. This gave the comet's icy core just enough time to shed mass gradually rather than explode catastrophically. As it passed through, onboard instruments revealed a breathtaking light show, vaporized material streaming behind it in a tail stretching 7 million miles, long enough to wrap around Earth 280 times, glowing brightly in ultraviolet as solar radiation excited its molecules. The aftermath revealed even more surprises. While Lovejoy lost an estimated 90% of its mass, its core remained cohesive enough to develop a new tail within hours, visible to backyard astronomers as it retreated from the Sun. This regeneration hinted at an unusually dense, rocky core beneath its icy shell, a structural quirk that may explain its survival against impossible odds. Subsequent analysis suggested the comet originated from the Creutzfeldt-Sungrazer family, fragments of a giant comet that broke apart centuries ago, with Lovejoy representing one of the largest and most robust remnants. For scientists, the event was more than a cosmic curiosity. It offered an unprecedented chance to study solar corona physics from a moving vantage point. As material boiled off the comet, it traced magnetic field lines normally invisible to telescopes, revealing complex structures in the Sun's atmosphere. The Solar Dynamics Observatory captured every moment, showing how the comet's tail kinked and twisted as it crossed regions of opposing magnetic polarity, a real-time map of the corona's invisible forces. Perhaps most remarkably, Lovejoy's saga didn't end there. Against all predictions, the comet returned 7 years later, having survived its first solar encounter only to complete another orbit. Though significantly diminished, its reappearance proved these icy visitors can endure far more punishment than we imagined. In a universe where cosmic destruction often seems absolute, Comet Lovejoy stands as a gritty underdog, a reminder that even the harshest environments sometimes spare the boldest travelers. Right now, an invisible hurricane is blowing through your body at 1.3 million miles per hour, a torrent of dark matter particles streaming through Earth like ghosts through a wall. This hypothetical phenomenon, called dark matter wind, arises from our solar system's motion through the Milky Way's halo of mysterious, gravity-wielding particles. While stars and gas orbit the galactic center, the heavier dark matter halo remains relatively stationary, creating a perceived wind as we plow through it, a cosmic headwind undetectable to human senses but potentially measurable with ultra-sensitive experiments. The concept isn't just theoretical theater. If dark matter consists of weakly interacting massive particles WIMP, as many physicists suspect, this wind could leave faint fingerprints when particles occasionally collide with atomic nuclei in underground detectors. The Dama/Libra experiment in Italy's Gran Sasso Mountain claims to have spotted such signals, an annual modulation in detection rates that aligns perfectly with Earth's movement into the galactic wind. As our planet orbits the Sun, its velocity adds to or subtracts from the solar system's overall motion through the dark matter halo, creating a windier season every June and a calmer period in December. Dama data collected over 2 decades shows this 6% fluctuation with striking regularity, like a cosmic metronome ticking to the rhythm of our galaxy's hidden currents. Yet controversy swirls around these findings. Other experiments, Xenon, Lux, and Panda X, using different detection materials, have found no corroborating evidence. Critics argue Dama signal could stem from mundane sources like seasonal variations in muon radiation or subtle shifts in the lab's environment. But supporters counter that Dama sodium iodide crystals might interact with dark matter uniquely, potentially sensing lighter particles other setups miss. This deadlock has birthed next-generation projects like Cosine 100, which replicates Dama methodology while aggressively ruling out false positives. Early results neither confirm nor refute the original findings, leaving the mystery wide open. The stakes couldn't be higher. If dark matter wind is real, its detection would revolutionize particle physics, offering clues about the invisible 85% of the universe's mass. The wind's direction could map the Milky Way's dark matter distribution, while its intensity might reveal whether dark matter clumps around galaxies like cream in coffee. Some theories even suggest the wind isn't uniform, that dark matter streams from devoured dwarf galaxies could create localized gusts like rivers merging into an ocean current. Imagine future telescopes seeing these flows indirectly through their gravitational lensing effects, or spacecraft navigating by dark matter currents as sailors once used trade winds. For now, the hunt continues in laboratories buried deep underground, where scientists listen for the faintest whispers of particles that may have shaped the cosmos since its birth. Whether Dahmer's signal proves true or not, the pursuit of dark matter wind has already reshaped our understanding, not just of what fills the universe, but how it moves, interacts, and hides in plain sight. Deep in the heart of the Large Magellanic Cloud, a cosmic nursery rages with activity so violent it makes Earth's fiercest hurricanes look like gentle breezes. The Tarantula Nebula, a sprawling stellar factory spanning 650 light-years, churns with gas clouds tearing through space at 100,000 miles per hour, their turbulent motions sculpting the birthplace of tomorrow's supergiant stars. This isn't just fast, it's star-forming chaos on an unprecedented scale, where gravity and turbulence wage war across light years, and newborn stars ignite in mere cosmic blinks compared to our Sun's leisurely 100-million-year gestation. At the nebula's core lies R136, a monstrous cluster where stars don't just form, they erupt into existence with startling speed. Here, collapsing gas clouds forge stellar behemoths hundreds of times more massive than our Sun in as little as 100,000 years, a staggering pace that defies earlier theories of slow, steady stellar growth. The secret, the tarantula's extreme environment, where supersonic shockwaves from nearby supernova compress gas into dense knots almost instantaneously. Picture a cosmic snowplow ramming through interstellar material, piling it into towering ridges where gravity takes over, igniting nuclear fusion before the newborn star can even stabilize. What makes this region truly unique is how its violence feeds creation. Hubble's razor-sharp vision reveals intricate tendrils of ionized hydrogen, some stretching 50 light-years long, whipped into frenzy by competing forces. Radiation from young, ultra-bright stars etches away at surrounding gas, while stellar winds blast outward at millions of miles per hour, carving vast cavities that glow in X-rays. Yet within this destruction lies the seed of new beginnings. The compressed edges of these bubbles become prime real estate for the next generation of stars, their material packed so tightly that gravitational collapse becomes inevitable. The tarantula's most famous resident, the star cluster NGC 2070, showcases this cycle in action. Nestled within one of the nebula's turbulent arms, it contains over 5,000 stars younger than 2 million years stellar toddlers by cosmic standards, including several so massive they've already exploded as supernova. Their short lives and violent deaths create a self-sustaining ecosystem. Each explosion injects new energy and heavy elements into the surrounding cloud, triggering fresh rounds of star formation even as it tears apart neighboring gas structures. It's a celestial Möbius strip where creation and destruction form an endless loop. For astronomers, the tarantula offers a rare glimpse into the universe's early days when conditions resembled this modern-day maelstrom. In the cosmic dawn, galaxies likely hosted countless versions of such extreme nurseries, their rapid star birth shaping the evolution of entire galaxies. Today, as we watch supermassive stars like R13601, a blue hypergiant 260 times heavier than our Sun, ignite amidst the chaos, we're witnessing the same processes that built the first stellar generations playing out in our galactic backyard. Yet even this breathtaking speed has limits. The tarantula's most massive stars burn so furiously that they'll exhaust their nuclear fuel within 5 million years, their deaths likely birthing black holes or neutron stars that will continue stirring this cosmic cauldron. As new telescopes like James Webb peer deeper into its swirling gases, they reveal another surprise. Some protostars here are growing so fast they might challenge theoretical upper mass limits, suggesting the universe still has tricks to teach us about how stars, and perhaps even the first quasars, were born. Racing toward the Milky Way at 150,000 miles per hour, the colossal Smith cloud is about to make a spectacular homecoming, one that will unleash a firestorm of star formation in its wake. This gargantuan river of hydrogen gas, stretching 11,000 light-years long and 2,500 light-years wide, carries enough material to birth 2 million suns. But what makes this hypervelocity cloud truly extraordinary isn't just its size or speed, it's the mystery of its origins. Is it intergalactic debris captured by our galaxy's gravity, or the explosive aftermath of a long-forgotten stellar catastrophe? Some 50 million years ago, the Smith cloud was hurtling away from the Milky Way's disk at nearly 700,000 miles per hour, fast enough to escape our galaxy entirely. Yet gravity had other plans. Detailed radio telescope observations reveal the cloud's trajectory bending into a perfect arc, like a cosmic boomerang, as the Milky Way's pull gradually reversed its course. Now, in about 30 million years, this celestial prodigal will come crashing back into our galaxy's spiral arms near the constellation Aquila, triggering shock waves that will compress interstellar gas and ignite bursts of new stars. The cloud's composition holds tantalizing clues about its past. Unlike pristine intergalactic gas, the Smith cloud bears traces of heavier elements, oxygen, sulfur, and even traces of iron, suggesting it originated from within the Milky Way itself. One leading theory proposes it was launched outward by a chain reaction of supernova explosions, a galactic cannon firing a gargantuan gas bubble into the halo. Others speculate it might be the tattered remains of a dwarf galaxy torn apart by tidal forces, its stars devoured while its gas lingered in this spectacular filament. Chandra X-ray Observatory's detection of a faint million-degree corona surrounding the cloud adds another layer to the puzzle. This shimmering veil of hot gas suggests the Smith cloud has been plowing through the Milky Way's halo material like a ship's bow wave, heating the surrounding medium to staggering temperatures. Meanwhile, its leading edge glows with the telltale signature of collisional ionization, evidence that the cloud's outermost hydrogen atoms are already brushing against our galaxy's tenuous outer atmosphere. What awaits this cosmic juggernaut upon re-entry? Simulations show the Smith cloud's impact will be anything but gentle. As it plummets through the galactic plane at a steep angle, turbulent interactions will shred its structure into tendrils, mixing its chemically enriched gas with the Milky Way's interstellar medium. The resulting shock fronts will become nurseries for massive stars, their intense radiation lighting up the spiral arms like a string of cosmic fireworks. Yet the most profound revelation might be what the Smith cloud tells us about our galaxy's ecosystem. Its trajectory suggests the Milky Way's halo is far more dynamic than we imagined, a place where gargantuan gas structures cycle in and out like celestial tides, redistributing the raw materials for star formation across galactic timescales. Each returning cloud carries elements forged in ancient stellar furnaces, seeding future generations of stars and planets with the ingredients for life. As the Smith cloud streaks toward its destiny, it serves as a reminder that even the seemingly empty spaces between stars teem with motion and drama. This isn't just an isolated phenomenon, it's one thread in a vast cosmic web of circulation, where matter expelled by violent events eventually returns, weaving new chapters into our galaxy's ongoing story of creation and renewal. Locked in a gravitational death spiral, the pulsar duo Pulsar J0737-303 9 whirls around each other at 600,000 miles per hour, so fast they complete a full orbit in just 2.4 hours. This cosmic dance floor stretches barely 800,000 miles across, meaning the two neutron stars could fit comfortably between Earth and our Moon with room to spare. What makes this binary system truly extraordinary isn't just its speed, but the precision with which it's proving Einstein right while racing toward an inevitable collision that will shake the very fabric of space-time. Each pulsar in this pair is a city-sized remnant of a supernova explosion, packing more mass than our Sun into a sphere just 12 miles wide. Their surfaces are crystalline crusts floating on oceans of superfluid neutrons, with magnetic fields so intense they could strip data from a credit card halfway across the solar system. As they spin, their lighthouse-like beams sweep across Earth every 23 milliseconds and 2.8 seconds respectively, an odd couple where one partner twirls like a frenetic ballet dancer while the other moves with the deliberate pace of a waltz. The real magic happens in the space between them. General relativity predicts that such closely orbiting massive objects should emit gravitational waves, ripples in space-time that carry energy away from the system. For Pulsar J0737-3039, this energy loss is staggering, about 7 million tons of mass converted to pure gravitational wave energy every second. That's equivalent to annihilating 14 Golden Gate Bridges worth of matter daily, not through nuclear reactions, but through the sheer distortion of space itself. Astronomers first detected this system in 2003, and it immediately became a Rosetta Stone for testing relativistic physics. The pulsar's orbital decay matches Einstein's predictions with uncanny precision, their mutual dance tightening by 7 millimeters per day, a rate that would make a sundial's shadow seem hasty. This gradual in-spiral isn't just academic, it's a countdown timer to one of the most spectacular cosmic events our telescopes may ever witness. In approximately 85 million years, a cosmic eye blink compared to the age of the universe, these pulsars will finally merge. The collision will unleash a gravitational wave burst so powerful it will briefly outshine all the stars in the observable universe combined. For perhaps 30 seconds, the merging pair will emit more energy than every star in the Milky Way produces over 30,000 years. The resulting kilonova explosion will forge enough gold, platinum, and uranium to outweigh entire planets, scattering these heavy elements across interstellar space at near light speeds. Yet the system's greatest gift might be what it's teaching us right now. By tracking subtle variations in the pulsar's radio pulses, scientists have measured effects like geodetic precession, where the spin axis of each pulsar wobbles like a top, and Shapiro time delay, where signals from one pulsar slow slightly as they pass through the other's gravitational field. These observations provide the most stringent tests yet of general relativity in strong gravitational fields, with every new data point either confirming Einstein's genius or hinting at physics beyond his theory. What's truly humbling is the timescale of this cosmic experiment. The pulsar's orbital decay is so gradual that human civilization may rise and fall before the merger occurs. Yet their steady, predictable dance gives us something rare in astronomy, a front-row seat to a cataclysm we can forecast with atomic clock precision, unfolding according to physical laws written into the universe's fabric. When that final collision comes, the resulting gravitational waves will ripple through space-time long after our sun has faded, carrying echoes of this pulsar pair's doomed waltz across the cosmos. At the heart of some of the universe's most violent environments, black holes don't just swallow matter, they spit it back out with unimaginable fury. These are relativistic disk winds, supersonic tornadoes of superheated gas screaming from accretion disks at 40% the speed of light, nearly 270 million miles per hour. Picture a cosmic hurricane where the winds don't just knock down trees. They could vaporize entire planets powered by the very forces that were supposed to drag everything into oblivion. Chandra X-ray Observatory's sharp vision has mapped these extreme outflows in stunning detail, revealing structures that defy intuition. When gas spirals toward a black hole's event horizon, friction heats it to millions of degrees, creating a swirling disk of plasma brighter than entire galaxies. But not all that material falls in. Intense radiation pressure and magnetic fields eject some of it in bipolar jets' collimated beams, while other particles get hurled away in a wider, chaotic spray. The result, a spherical wind of ionized atoms racing outward fast enough to cross the diameter of Neptune's orbit in under an hour. One of the most studied examples lies in the quasar PDS 456, where Chandra detected ion atoms, usually a tracer of cooler gas moving at these relativistic speeds. This discovery turned assumptions upside down. Normally, such heavy elements shouldn't survive the disk's extreme heat, let less be accelerated to such velocities. Their presence suggests these winds originate farther from the black hole than previously thought, where temperatures are just low enough for iron to retain some electrons. The atoms act like cosmic speedometers, their telltale X-ray absorption lines stretched and skewed by the Doppler effect, revealing velocities with precision. What's truly counterintuitive is how these winds shape their own destruction. As they blast through surrounding gas clouds, they create shock fronts that heat the interstellar medium to X-ray emitting temperatures. Paradoxically, this process can stifle star formation across entire galaxies by sweeping away the cold molecular gas needed to birth new stars. Yet in some cases, these same shockwaves might trigger star formation by compressing nearby gas pockets, an astrophysical case of creative destruction playing out on a galactic scale. The energy budgets here dwarf anything in human experience. A single relativistic wind can carry kinetic energy equivalent to the mass of several suns converted entirely to pure motion. That's enough power to reshape not just the host galaxy, but its surroundings for hundreds of thousands of light years. Some models suggest these outflows might solve a long-standing puzzle: why the universe isn't swimming in supermassive black holes. By expelling massive amounts of gas before it can be consumed, the winds effectively put a brake on their own growth while regulating the evolution of their galactic homes. Recent simulations add another twist. These winds might be clumpy, not smooth. Dense knots of gas embedded within the outflow could explain why some observations show uneven absorption features, like cosmic bullets firing through a fog. This structure makes the winds even more efficient at transporting energy, as the denser regions punch through interstellar material while trailing turbulent wakes that mix heavy elements far into intergalactic space. The implications stretch beyond single galaxies. When multiple relativistic winds from different black holes intersect in galaxy clusters, they can create vast cavities in the hot intracluster gas, visible in X-ray maps as eerie, dark bubbles. These voids aren't empty. They're filled with magnetic fields and cosmic rays accelerated by the wind's passage, creating particle accelerators on scales no human machine could ever match. Every new observation peels back another layer, revealing how black holes, often portrayed as ultimate destroyers, are also architects shaping the cosmos with winds that carry the echoes of their ferocious appetites across space and time. No matter how fast pulsars spin or how violently quasars erupt, one cosmic rule remains unshakable: nothing can outpace light in a vacuum. Einstein's special relativity laid down this law over a century ago, declaring light speed the universe's ultimate speed limit at 186,282 miles per second. This isn't just some arbitrary restriction, it's woven into the fabric of reality itself. As objects approach light speed, their mass balloons toward infinity, requiring infinite energy to accelerate further. Even the most energetic particles from gamma-ray bursts, hurtling at 99.9999% light speed, still fall just short of breaking this barrier. The cosmos enforces this rule with absolute authority, no matter how powerful the explosion or how extreme the gravitational slingshot. Light speed remains the finish line no runner can cross. Yet here's the cosmic curveball: while objects can't move through space faster than light, space itself has no such limitations. During the universe's first fractions of a second, cosmic inflation stretched the newborn cosmos exponentially, expanding it 100 trillion times in less time than it takes light to cross a single proton. This wasn't motion through space, but space itself being created between points, carrying them apart at effective speeds dwarfing light's. Today, dark energy continues this trend on a grander scale, pushing distant galaxies away so fast their light will never reach us, not because they're moving, but because the space between us grows faster than their photons can traverse it. Imagine two ants on an inflating balloon. No matter how fast they crawl toward each other, the balloon's expansion can separate them faster than their tiny legs can compensate. That's the essence of faster-than-light cosmic expansion. Distant galaxies aren't breaking any speed limits, they're fixed in their local space, but the stretching fabric between us creates the illusion of superluminal recession. This subtle distinction resolves one of relativity's greatest paradoxes, allowing the universe to grow vast without violating its own laws. What's truly humbling is realizing how these two phenomena, light speed's inviolability and space's unrestrained stretching, define our cosmic horizon. Light speed ensures causality, preventing effects from preceding causes across the universe. Meanwhile, inflationary expansion explains why we see a uniform night sky despite distant regions never having exchanged heat or information. Together, they form the yin and yang of cosmic structure, one enforcing order, the other driving growth. A delicate balance that shaped everything from the formation of atoms to the distribution of galaxies. So while black holes might bend light and quasars blast matter to near light velocities, the universe's ultimate traffic cop remains undefeated. Every hypervelocity star, every relativistic jet, every gravitational wave serves as a testament to this unbreakable rule, and the astonishing exceptions carved into the expanding canvas of space itself. The cosmos may be vast, strange, and violent, but it plays by rules even its most energetic citizens cannot break. From pulsars spinning hundreds of times per second to quasars blasting matter at nearly light speed, the universe is filled with objects that defy our earthly notions of motion. Let's revisit the top 5 most extreme velocities that showcase the cosmos' breathtaking power. First up, the record-holding pulsar PSRJ 1748-2446 AD, rotating 716 times every second. Imagine a city-sized stellar corpse spinning so fast its surface moves at a quarter the speed of light, held together only by gravity stronger than 100 billion Earths. Then there's the terrifying velocity of quasar outflows, where supermassive black holes hurl storms of superheated gas at 40% light speed, enough energy to reshape entire galaxies. These aren't gentle breezes but cosmic tsunamis carrying the force of a trillion suns. Don't forget hypervelocity stars flung from galactic centers at over 1 million miles per hour by black hole slingshot stellar fugitives destined to wander the void between galaxies. Or the mind-bending gamma-ray burst jets where particles scream through space at 99.999% light speed, outpacing their own explosion's light. And who could ignore the oh my god particle? A single proton from deep space that struck Earth's atmosphere with the kinetic energy of a fastball crammed into a subatomic speck, moving so close to light speed that time nearly stood still for it. Each of these phenomena reveals a universe far wilder than fiction, where gravity, magnetism, and sheer cosmic violence conspire to push matter to unimaginable extremes. Behind every staggering speed lies a story of creation and destruction, from neutron stars forged in supernova to black holes shredding stars into hypervelocity projectiles. These aren't just curiosities for astronomers, They're proof that the cosmos operates on a scale of energy and motion we're only beginning to grasp. What's your favorite cosmic speed demon? Maybe it's a rogue planet ejected from its star, or colliding galaxy clusters sending shockwaves through intergalactic gas. Drop your picks in the comments. We're just scratching the surface of the universe's need for speed. And if you're hungry for more cosmic mysteries, hit subscribe to explore the universe's most mind-bending wonders. After all, out there in the darkness, something even faster might be waiting to be